Hey guys, so we're going to talk a little bit about the penny and the sand, rocks, and gravel deal, as well as the cork. It's going to all kind of come together, but the first thing we need to talk about is the particle interactions in a water molecule. So what we're looking at, remember, we're going to come back to kind of this idea of the penny and the water that stayed on top of the penny, and then we're also going to talk a little bit about the cork. So in a glass or whatever, why did the cork go to the edge over here, right? So we're going to work up to that in just a minute. Before we get there, we've got to talk about some other things. So first thing is we need to probably define what a force is, right? And in physics, you should have learned that a force is a push or a pull on an object. So if we can push an object, then we're applying force to it. Remember, force is what causes objects to move. They don't have to move for it to be a force, but it is what is applied to them, and then that's what makes them move if they do. So if we know what a force is, which is a push or pull, then we can start talking about these interactions in terms of attraction and repulsion, okay? But before we get to that, let's go back and just real quick look at the water molecule again. Remember, it's the dead polar bear. So we have the O, the H, right? And then the X's are eyes, mouth, right? And then there's two lone pair electrons. Those aren't terribly important right now for what we're doing. Remember that this is the partial positive side because of the X's for the eyes. And then this is the partial negative side because of the minus on the mouth. So if we're looking at this, what we really need to be concerned about before we go too much further is really going all the way back to chemistry. So if I have oxygen, remember, valence electrons go on the outside, and its valence electrons would look like this. Oxygen has 6 valence electrons. You pair them up first, and then you go back and get the others. Then hydrogen is going to look like this. I'm going to draw it with an X just because we're going to bond them here in just a minute. So you can see when I have 2 hydrogens, one will go here and one will go here, right? That puts in a hydrogen here and a hydrogen here. Then if we want, when we were working with chemistry, we can go back in and we can call those bonds, right? And so if we look at that, basically what I just drew was this guy right here. So if I flip the orientation of that, I have my lone pairs here, and opposite those lone pairs become my hydrogen bonds. So these bonds right here, remember, resulted from the sharing of electrons. And when we share electrons, that is called a covalent bond, which occurs between 2 nonmetals. So if we know that a covalent bond is within the molecule, that covalent bond is a force. It requires a lot of energy to build that bond, and it requires a lot of energy to break that bond. If I were to come in and break that bond apart, I would have to break this up. So it would be H2O. I would have to do something very interesting to it, and I would have to break it up into H2 and O2. The only way I can do that is a process called electrolysis, and that produces hydrogen gas and oxygen gas. If I wanted to take those two and create water, then I would have to have a spark come near those. That would be an explosion, and then the result would be some water vapor. Now, what's important about that is basically we just need to understand that in order to break these bonds, it takes a lot of energy. And really, we're not going to see that unless we're doing something really, really important. So when we go and talk about this water heating lab, we're not breaking these covalent bonds. We'll talk about that a little bit later. So let me erase some stuff here, and then let's get into this attractive force stuff. So if we have our dead polar bear, right, and we have a positive side and a negative side, then we should remember from chemistry, from physics, that opposites attract, and then likes repel. And if we know that, then if we have a water molecule, right, it's like this, these are the H's, this is the O, we know that this is minus, this is plus, right? If I have a water molecule that is nearby, it is arranged like this, plus, minus, right, then there is going to be an attraction here, right, because there's a minus and a plus. So this will be an attraction, right? So an attraction is a pull, right? Then let's look at what a repulsion would be. You should probably already be figuring this out, but if I have a minus here, and let's say I have a minus here, these guys right here are going to repel. A repel is going to be a push. So we have the water molecule can attract or repel. That means it can push or pull each other, and the result or the reason for that is because a water molecule is polar, the dead polar bear, right? So let's stop there, and then I'll come back in just a second. Okay, so let's talk about this penny and this cork. They are both having to do with the same thing here. And basically what's going on is with the water. So on the penny, we're just looking at the water. And then in the glass, we're actually looking at two things going on. And those, basically the same idea or concept is at play here. And it has to do with those attractive forces that are in water. Notice I did not say the repulsive forces that are in water. So if we just look at this water, I kind of gave you these two together because really these two sort of, this one kind of gives you the answer to this one. So let's start with this question. Where, oh sorry, let me get my, there we go. Where will a cork float in water? So if I had, let's just do this. Let's say I have a cup of water. It's filled up to here, and I have an identical cup. It's filled up to here. So where will the cork float in water? This isn't a trick question. You would answer that the cork would float here in this one, and it would float here in this one. So this one compared to this one, where is the cork floating? It's floating at a higher point. So the cork is also always going to float at the highest point. So let me ask you this. Where would the cork float in this particular case? If you look at this, it should float right up here, right? And if the cork floats right up there, then we are basically looking at the cork floating at the highest point. So when we look at this glass thing, the reason that you had trouble getting it to float in the middle is because when you look at glass, this might jog your memory. When you look in a graduated cylinder, right, and you look at the water line in the graduated cylinder, it does this, right? And what do we call that? We call that, if you remember, well, not that. We call that a meniscus, right? And so what's going on in this little spot right here is what's really important. This is now the highest point, right? So right there, you can see it in this blown up version over here if you want. Right there is the highest point. So if I were to drop a cork in here, so let me just change my color here. Say I drop a cork in right here. Gradually over time, it's going to slowly go to the side and then float right here because that is the highest point, right? So in this glass of water, the reason the cork seems to be attracted to the glass is because it's actually just moving to the highest point of water. So if you wanted to get your cork to float in the middle, you would have to fill your glass up so that it is completely over the rim with water. And once you do that, the cork would then come back to the middle. Now, why does water do that? Usually people throw out the word surface tension, right? Surface tension. Which, if you say that, I mean, you're right, but what causes surface tension, right? And that's what we really need to understand. So if you can imagine all of the water molecules in this water dome on the penny, right? Basically what's happening is attraction, right? So we've got molecules that are basically holding hands. Remember in that last video I told you that it's kind of like red rover, right? So basically if these guys can get together in such a way that they are going to align themselves and attract to each other, then they're going to be essentially holding hands. And when they hold hands, that force is strong enough to resist spreading out. So just like red rover, if something comes and tries to strike between two of those, more often than not, it will bounce off and it can't get through, right? So there's this surface film of molecules that just sits kind of on the surface and holds hands and keeps everything compact and working together. So it is that attraction between water molecules that is what's holding it together. So surface tension is the attractive forces between molecules help keep the substance from spreading out, right? And in water, it's actually an attractive force between water molecules. So if that attraction between two molecules, so if that attractive force is between two molecules of water, that is called a cohesive force. Right? So I'm going to pause there for a minute. Okay, so we said cohesion. Cohesion is the attraction between two water molecules, right? So you're probably wondering, well, why doesn't, in this glass scenario, why doesn't it form a dome then? Well, it's because there's another type of force. There's another type of force called adhesion, right? And adhesion is when a water molecule is attracted to non-water molecules. Now, usually that means that the molecule that it's attracted to is slightly polar, like water, because there can be those positive and negatives and there can be attraction. So if we look at glass, the reason I told you it had to be in a glass and not a plastic cup is plastic is non-polar. So if you did this in a plastic cup, chances are you would get a dome of water in here. You would get an inverted meniscus. In fact, if you've ever looked at a plastic graduated cylinder, you'll actually see that the meniscus inverts. And instead of reading at the bottom, you would actually read that meniscus at the top. But here's what's going on. So basically, if we look at adhesion, adhesion is when water is now attracted to another molecule other than water. So you have the attraction to all the water molecules in here, but then you also have a dude that's grabbing the glass, basically, and it's going to try to pull its way up the glass. And as it does that, other molecules are going to be pushing on it and pulling on it and pushing on it and pulling on it. So you get this creeping up the edge of the glass, and it's basically trying to work its way up the glass because it's attracted to the glass. So that is adhesion. And you think of adhesion, tape, you stick it to something. I always say, when I'm trying to remember these two words, co means together, two things usually together, which in this case, co is two waters, right? And then ad usually means without together. So they're not the same thing, but they are together in the adhesion part. But anyway, the ad and co, I always think of adhesion, tape adheres to surfaces, right? Tape is one type of thing and a wall is another type of thing. So adhesion is when two non-similar things stick together, and then cohesion is where two similar things stick together. So water to water, co, water to something else, adhesion. Now, if we were to then apply this elsewhere, we would then be able to start to look at, well, what happens if water can climb up and then let's say it continues to climb up, then that's going to be a different thing that has to do with our rocks and our sand and gravel demo. So I'm going to stop this here, go over to that, and then we'll kind of see what we've got going on over there.